Today in this video, I'm going to teach you how to convert a 12 volts car alternator to 36 volts. This one that you see is a 12 volts car alternator now without any transformer or any additional circuit or winding change. I'm going to convert it to 36 volts, and the best part is that it is going to produce 36 volts at the same RPM at which it used to produce 12 volts. So let's get started. Now guys, here you can see two car alternators, one with the voltage regulator and three-phase bridge rectifier, and the other one without any voltage regulator or rectifier. Now the difference between the two is this one is going to produce a max of around 14.4 volts DC, but this one can produce much more voltage depending upon the RPM. Higher the RPM, more will be the output voltage. So if you also want a lot more voltage than 14 volts, then you will have to remove the bridge rectifier as well as the voltage regulator, and make sure that you do not remove this brush case. It holds the brush that feeds electric current to the rotor inside the alternator. So in this video I'm going to work on this one because it does not has the rectifier or the voltage regulator. So let's remove this one. So guys, after you have removed the rectifier and the voltage regulator, you will be left with 6 wires, and 2 of which are going to be the brush wires feeding the rotor, and that will be separate. You can see that these are the slip rings for the rotor winding of the alternator, and they are usually going to be colored as shown here, red and blue. Now there is a possibility that you might see only 3 wires instead of the 4. That depends if the 3-phase armature connection of the alternator is in star or delta. If you have 4 wires, then you will have to keep 1 wire, which is the neutral point, disconnected. It is going to be the tapping point for all the wires, because of which it is going to be very thick, so it can be separated easily. And the remaining 3 thin wires, when compared to the thick one, are going to be your 3-phase final output wires. Now in case of delta connection, you don't have to worry about the thicker wire, which is the neutral point in case of the star connection, because there is no neutral point in delta. So these 3 wires are the 3-phase. Now comes the part of removing this back cover of the alternator. Seems like I will have to use the manual method. So guys, your question for today is, what was the power rating of the motor I used in my previous video? Now after removing the screws, you will need this minus type of screwdriver, and then try and open. Yeah, finally it is out. You can see the brushes. Yeah, that's the lower bearing, looks smooth. Okay, so these are the final output terminals coming out from the armature winding, and we have to work upon these. First you have to take out the insulation from the star connected neutral point. After that, you can see here that that all the wires are coming and joining at this point, which means that this one is the neutral tapping point for the star connected armature winding. So we will have to disconnect them all. Now for those of you who would like to watch the video in which I have removed the rectifier from the alternator and the voltage regulator, a link will be provided in the description, so don't forget to check it out. So first you have to remove the soldering of this tapping point. Yeah, one is out. So guys, the disconnection part of all the wires has been completed. Now comes the part of finding out which wire belongs to which phase. Now guys, I'm going to use 3 different colored wires for each of the phase, and I'm going to make a pair for each phase. So this wire, and this wire, these three were the initial output wires of the alternator. So I'm going to connect these three wires to these three terminals. Starting with this red wire. Now yellow. Yellow also done. Black also done. Yellow done. So guys, now comes the part of phase separation, for which you are going to need a multimeter. So here I'm going to point it out to this beeping mode, which is going to indicate the connectivity. So first, finding out the phase for the red wire. So let's leave out the yellow. Red connected over here, you see. Now out of these three, one is going to be the wire at which this multimeter is going to beep. Let's see this one. Nothing. Nothing. Yeah, this is the one, you see. So the starting wire for the first phase, which is red, and its end point is this one. So another red wire will be soldered at this point, and this will make one pair of phase. So these three denote this wire, okay, and the middle one is this one, and this piece that you see small, this is this one. Now we have found out that the extreme left one, which is the smaller one, is red, so denoting it by R. Now finding the connectivity for yellow, and I think the high probability is for the middle one. Yeah, got it. Middle one is yellow, so it's Y, and the remaining last one is going to be black. So the phase separation is complete. All we have to do is solder the respective wires, red, yellow and black, and that's it. So guys, now comes the phase rectification part. Here I'm going to use 3 bridge rectifiers, KBPC 3510 KBPC. So this is a metal piece on which I'm going to place all the rectifiers. I have not placed the paper tape, double-sided tape over here, because I'm going to place a screw through this and then connect it to the alternator itself, which is going to hold this entire piece in one place. So let's start with the connections of the rectifier to each other. This, what you see, is the +1, so the diagonal opposite is going to be the minus, which is negative. So negative will be connected in series and directly to the plus of the other, and then again negative, diagonal opposite as negative, will be connected to the plus of the other, and the final output will appear on this positive and this negative. This way all the rectifiers are going to be in series. So guys, now comes the part of connecting the final output wires. This terminal that you see is the positive. So red wire will be connected over here, and this one that you see, since this one is positive, so it's diagonal opposite. This one is the negative, so black wire will be connected over here, and these two will be the final output from the alternator. Red positive, black negative. Yeah. Now it's time to install the rectifier set. Yeah, so the rectifier set has been placed, and finally comes the part of connecting these armature wires to the rectifier. So first I'm going to start with red. This is the first one. Next comes yellow. And finally black. So let's solder the phase connection. This terminal that you see, this one, red will be connected. Yeah, now the other one. Done. Now comes yellow. Other yellow. They are also done. Black. Black also done. So all the wiring is complete. Final output is on these two wires and excitation is on these two. So let's start with the testing part. So guys, this is the car alternator, and I've connected the rectifier as you have already seen, plus these two wires that you see, the red and black jumper cables. These will be connected to this 12 volts battery for the excitation of the rotor inside the alternator. And with that being done, I have to rotate this rotor or the pulley of the alternator at a high RPM, after which it is going to display the generated voltage here on the multimeter display. Now let's feed electricity to the rotor winding of the alternator, connecting this final terminal to the battery, and then you will see actual voltage. At present it is producing around 9 volts DC. Let's increase the RPM. Okay. Here we are doing around 18 volts. Peaking at around 24 volts. 27. 36 volts. So guys, as you saw that this car alternator actually produced 36 volts DC, which was pretty insane because a car alternator cannot produce more than 14.4 volts. And if you want more voltage and more output, this is how you can do it. So guys, I'm going to start with this 12 volts bulb. Let's test and see how this one performs. Bulb has been connected. Connecting the battery. You can see guys, the bulb has started glowing. Let's increase the speed. Pretty good, right? Let's turn off the lights. Very bright. Superb. Turning it off now. So guys, that was about converting this alternator from 12 to 36 volts. Let me know in the comment section if you understood this project completely and you liked it. Hi guys, this what you see is a microwave plate motor and it can produce up to 220 volts easily. Generating electricity with these is really easy. All you have to do is connect this crank on the shaft of the synchronous motor and then it is going to produce 220 volts on these two terminals. Cool, right? So simple cranking, and the higher the rotation RPM, the more will be the output voltage and power. So amazing and easy. I got shocked. Now the output voltage was very high even though the RPM was so low. Why is that? Let's look inside it. Well guys, the bad news is that I was trying to open it, but unfortunately I think I broke it. That's the gearbox inside, because of which the RPM was very high even though I was rotating at such a low RPM. And that is why I got electric shock. You see so many gears, it's a reducer gear motor, but the motor got damaged. Well, how to proceed further? Luckily I have another piece, so no worries. And these are really cheap. Okay, microwave plate motors, they are really cheap, available readily in the market. Let's open it further. That's the thick and main gear, final driving shaft. And after that there are so many gears inside. Here you will understand these projections that you see, these are going to act as poles to the coil, and this is the magnetic rotor inside. And here is the clip. It's taking it. So this is the magnet, and inside this you will see around 4 poles. Only 4 poles are there, and the remaining 4 poles are on these. This one, this one, this one, and this one, and these go to the empty slots, and this is the winding. So I've removed the coil. You can see here the coil inside, so thin copper wire has been used with so many number of turns, and only 2 wires are coming out of it, making it a solenoid. And this what you see is the body that contains 4 of the 8 poles. So what happens is when this magnet is like this, so this is north, this is south, then again this is north, this is south, this empty space is north, this pole is south, empty space north, and this pole is south. So this entire metal piece becomes north. Let's assume it, if this piece of the magnet is north, and these poles will go to the empty space here, so they all will become south. This way it is going to convert a rotary magnet into a linear magnet, just like it is going inside and coming out at a very high RPM. Actually, the problem is that they needed a rotary motion instead of a linear motion. It is much easier and also not shaky. It is pretty good. So understand it this way, that the coil goes inside like this. And let's assume the part of the magnet that is facing the metal poles is north. So at present, the lower portion of the coil is north and there are no poles for the upper portion. And initially the upper portion was also connected somewhat like this. Then the upper portion of this coil will also become south. Then it will be a complete linear motion, north, south, and when this magnet rotates, then upper one becomes south and the lower one becomes north. And this happens really quickly, because of which this solenoid keeps on getting changed polarity, north, south, north, south, north, south, and thus it generates electricity because of the changing magnetic poles. Working of a synchronous motor is really simple. This is a synchronous motor with a clip attached to the shaft, and here we have a 220 volts AC source. So all we got to do is bend the terminals and place them in the socket and then turn the switch on. And this is very dangerous because it is 220 volts supply. Okay. Yeah, you see, it is running at a very low RPM. Well guys, I would like to see if it can shock me. The entire outside body of this motor is metallic because the coil was like wound on a plastic material. It was no way in contact with the body, but sometimes it still happens. Okay. Oh, it is shocking me. Once again. Not this time. It's not shocking me anymore. Yeah, I don't know why is that. At the first time it shocked me. You see, I'm touching it continuously. But there is a lot of vibration. So guys, here this is connected to the shaft of the motor and multimeter pins have been connected to the motor terminals here, as you can see. And now I'm going to run this motor with this, and you can see the display over here. As high as 483 volts AC. Now guys, let's connect this 220 volts 100 watts bulb to this generator and see it glow fully bright. What am I doing? Well, of course it would not work. This is 100 watts and this is only 5 watts. That would be really stupid, and it's not like I'm making free energy video over here. But now I'm going to connect an even bigger power, 200 watts LED panel. Light has been connected to the generator. Now let's rotate the shaft. Pretty good, right? Now guys, why is it that I said that this 100 watts bulb is not going to glow but this 200 LED panel is glowing? That is because this has a circuit installed, because of which when the power coming to the LED panel is low, then the LED panel will glow, but it is going to be like really dim but still visible, which is not the case with this 100 watts bulb. Now guys, instead of this big 200 watts panel, if we just try this 5 watts LED bulb, okay, then because the ratings are identical, 5 watts and 5 watts, this should glow pretty good. So let's try that. Okay, you see, yeah, it's glowing. Now let's turn off the lights and then see. You see that it is glowing really bright. Such a small motor and still it is glowing this 5 watts LED bulb so bright. You might see in the camera that the brightness is really high, but that is not the case in reality because I'm seeing it here right now. You see, you might see that it is glowing like really bright. It is like half the brightness of the original because half the power is only being fed to the bulb, but still it is a pretty good demonstration and good for college projects and useful. Try not to go pretty strong on this motor because the gears are of plastic or nylon, so they are going to break easily and then you might just damage your entire project. So guys, with that I'm finishing off the video, part 1 video on synchronous motors being used as generators. Today in this video I'm going to make a really powerful electric generator with this angle grinder. Now you might be thinking that yes, I have already made a video on that. I want to tell you that this video is different because in the previous video I used a small 3.7 volts battery which was used to excite the armature and the field coils of the motor of an angle grinder, which is not going to be the case this time. This time I'm not going to use any battery or any circuit, and still it is going to generate full power output. The most important point is that the motor inside this angle grinder is universal motor. It's not DC motor, it's not induction motor. So this technique that I am applying here with this machine is also going to apply on your mixer motors or some washing machine motors. So guys, this is the angle grinder, and if you see the label, it's showing 850 watts, 220 volts and 11,000 rotations per minute. And let's give it a spin. Here's the switch. So guys, for this you are going to need a working angle grinder, not a dead one. So let's start with the changes that you have to do to turn it into a generator. So the first part is to remove the disc if it's installed. Now these two, what you see are pulley like things, and I got them from a car alternator, and I'm going to use these two to fit the shaft of this angle grinder. One goes like this, the other one, sorry, this, and the other one like this. And this time this will be connected in the opposite direction. Okay, got it. Seems fine. Let's give it a spin once again, holding it tightly. Yeah, working as expected. Now comes the part of turning it into a generator. So the second part is to disconnect it from the mains power supply, which is obvious. Now guys, with that being done, take the wires of this angle grinder, these two wires, and connect it directly to 6 to 12 volts or even 20 volts load. I'm going to use this bulb. Two wires are here and two wires are here. Simply connect them together. Yeah, that's it. In my previous video you saw me connect a battery in series with the load, which is the bulb, and the 2 wires of the angle grinder. At present, that is not the case. Turn on the angle grinder and it should light up. Look closely. Did it light up? Of course not, because you have to cross the threshold voltage that it is going to generate. Before that, it is not going to produce any electricity. That was the main part of this video. So at a certain specific RPM, this universal motor starts becoming an electric generator, not before that. Now I'm going to carry on the same process but with higher RPM. For that, I have this thread. This time the RPM is going to be much higher than the initial spin. Let's pull it. This time the RPM is going to be high. You saw? Let's try it once again. Cool, right? Now let's turn off the lights and see how bright the illuminance is. So guys, the lights are turned off, as you can see. Okay, you saw how bright it was. It was really bright, and the efficiency of it when being used as an electric generator is very good, very good. Now guys, I know what few of you are going to do. They are going to pause the video right here and go and find out an angle grinder. If they can't get an angle grinder, they will find a universal motor, because in the video Mr. Electron said that an angle grinder contains a universal motor. So this technique is going to apply on this universal motor also, and they will get some universal motor, maybe a sieving machine motor from their grandmother, and then try to convert it into an electric generator using the same technique. So let's do that. Bulb connected, motor here. Let's wound the thread. And now they are going to be really happy because they are going to see this bulb glow. Okay, excitement level highest. Go. Oops, the bulb did not glow. Mr. Electron is a fraud. Maybe he is lying. Maybe he somehow hid the battery inside that angle grinder. If you would have watched the video completely, you wouldn't have been saying this. And the first thing that they are going to do after doing this test is go to my video and write a comment, negative comment, fake video. The problem is, guys, you have to watch the explanation also. Now, a universal motor can be used as an electric generator if the armature and the field winding uses thick copper coils with low resistance, overall resistance. Now I'm going to show you with the circuit how it works. So guys, the explanation behind it is this diagram that you see. It is of an AC/DC series motor, which is a universal motor. This piece that you see is the armature, and this piece that you see is the field winding. Although a universal motor has two field windings, but this is just a diagram, so I'm showing only a single field winding, and both the two windings are connected in series. Here you see this one is connected in series with the armature or rotor, and these two terminals are the final output terminals. Any other device that you have, or a machine part, mechanical part that you have, example a screwdriver, it has residual magnetism, and your drill bits, they also have residual magnetism. Now these are two clips and this is my drill bit. Here you will see residual magnetism. You see that it is dragging it little by little. So that's the residual magnetism that I was talking about. Now, because of previous operation, some residual magnetism is always left in the motors, which is being utilized here in this universal motor. This is the armature, and let's assume that the motor was stopped at a point, like the switch was turned off at a point such that the poles stop with residual magnetism of north over here and south over here. Now when this rotor or this armature or rotor is rotated at high RPM or run at high RPM, residual magnetism is going to induce EMF in the field winding, because of which some voltage is going to appear on the final two terminals, which is going to be very low. Now when you will connect a 12 volts bulb in between these two terminals, that low current is going to flow through the 12 volts bulb. After that comes the second phase, and in the first phase the current is flowing through the bulb, but still the bulb is not glowing because the power generated by the residual magnetism is very weak. Understandable, right? Now that small current is going to enter the armature winding also, since the armature winding is connected in series with the field winding. Now that additional current is going to boost the pole strength, residual pole strength, and turn them into stronger poles than they were before, because of which more EMF is going to get induced in the field poles and more current is going to flow through the same 12 volts bulb connected initially. Now comes the second phase, in which more current is flowing through the bulb. So there is going to be an exponential growth in current and the bulb will start lighting up slightly. The current is going to enter the bulb and then again enter the armature, and this time even more current is going to fed to the armature poles. So again the armature poles are going to get really strong and more EMF is again going to be fed to the field poles, and this process is going to repeat until it achieves full pole strength, magnetic strength on the poles, and the bulb starts lighting up really bright. And what is this entire magnetism and induced EMF going to depend upon? It is going to depend upon the RPM at which this armature or rotor is being operated by an external power source, which was my hand. In case of the angle grinder, if you are going to use some external machine, then that is going to be the driving force. So higher the RPM of the armature, more will be the EMF induced in the field poles and more will be the current flowing through the bulb and thus exciting the armature once again. Now guys, there is one question that arises: why did I use only a 12 volts bulb, a low voltage bulb, and not a 220 volts or a higher resistance bulb? Now guys, that is because a higher voltage bulb generally has higher resistive value. Now guys, let's assume that around 1 volt gets induced in the field winding. Now because of the connected high voltage bulb or high resistive load, very less current is going to flow to the armature winding of the rotor, which is our main priority, because that current is going to increase the residual strength of the magnetic poles and make them even stronger poles to turn it into a powerful generator. Now that process will be eliminated because of the high resistive load being your 220 volts bulb. Now guys, some of you might be thinking that why is it that the residual magnetism is available only on the armature poles and not on the field poles? So guys, that is not the case. Residual magnetism is also available on the field poles, but still it does not matter because the result is still going to be the same. There is going to be a fight of magnetic pole strength between the field poles and the armature poles. Whichever is going to win is going to override the other one, and thus the same process is going to follow.